Muy bien, vamos a dar paso ahora al primer bloque. En este bloque vamos a tener como objetivo los desafíos de la transmisión en la transición energética. Ya lo que comentó Carlos, vamos a ver en la práctica cómo, tanto en Chile como en el caso particular de Estados Unidos, estamos enfrentando estos desafíos, cómo están afectando a la red de transmisión, cómo nos podemos preparar. Y para ello tenemos dos invitados y dos invitadas. En primer lugar, voy a dar el paso a la presentación de nuestro invitado internacional. Él es Stephen Solis, de ERCOT. Are you there, Stephen?
Yes, I'm here. Are you able to hear me okay?
Oh, yes, very good. Nice to meet you, Stephen. Thank you very much to participate in our seminar. I'm going to introduce you briefly for the different attendants. Stephen tiene un bachelor en ingeniería eléctrica de la Texas A&M University en Kingsville. Él trabaja en ERCOT, que es el operador independiente del sistema eléctrico de Texas, en Estados Unidos, donde él es, desde el año 2008, que ingresó, es un principal en System Operations Improvement. Ha trabajado también en varios grupos de trabajo, por ejemplo, de la NERC, de la North American Electric Reliability Corporation, en aspectos que tienen que ver con operación, otros grupos también regionales, con los distintos participantes del mercado, donde ha analizado distintos temas operacionales y también lecciones aprendidas. En forma previa a su trabajo en ERCOT, también estuvo 6 años en aspectos operacionales y técnicos en centrales a carbón. Then, please, Stephen, you may share your presentation with our participants.
Okay, are you able to see the presentation?
Yes, very good.
Okay, well, I'll get started. As mentioned, my name is Stephen Solis. I'm a principal of System Operations Improvement for ERCOT, the Electric Reliability Council of Texas. I'm going to be speaking with you today about a disturbance that occurred on the system on May 9, 2021, that we refer to as the Odessa disturbance, just because of its general location. When we look at this particular event, it was a single phase to ground fault on the lightning arrestor right outside of a natural gas unit. It was a normally clearing fault, 3 cycles. So as expected, the unit tripped off. But what was unexpected is the amount of other resources that reacted negatively to that event. In particular, 18 different solar sites and 3 wind sites saw a tripping of their inverters or a temporary reduction in megawatts in the order of about 1,148 megawatts of unexpected generation loss due to that disturbance. Because of that, we did see a frequency disturbance. We were able to recover rather quickly, but this was unexpected and caused some amount of alarm. When we look at the geographical dispersion of the impact of this disturbance, from that single fault, we saw solar units as far as 200 to 300 miles away, all across different kV levels, react negatively to that disturbance. We have 138 kV, 69 kV, and 345 kV as our nominal transmission backbones. And on each of those kV levels, we saw solar units trip off or temporarily reduce the megawatts. And we saw it at different time frames, meaning some responded where they dropped off megawatts, but recovered within 10 seconds. Others took a little bit longer to come back, maybe within a minute. Others between 1 and 5 minutes, and some quite farther beyond that. So when we looked at the megawatt recovery, it was not as expected. We would like to see them come back if they had to temporarily reduce within a second, so that perhaps they're trading some reactive power, some real power for reactive power to bring back the voltage on the system. But generally, we would expect them to come back within 1 second. Obviously, those that were impacted took much longer. Now, when you compare with the wind resources, they didn't see quite as many issues. And we'll talk more about that understanding that we have there. But you can still see we did have some inverter-based resources at wind sites that had negative effects due to this particular event. When we look at the causes, and I want to pause here and take a little bit more time on this slide. The primary or leading cause that we saw as far as impact were really two things. One was PLL, loss of sync relays, or phase lock loop protection that really shouldn't have tripped off those units, but we did see that we had about 389 megawatts of lost generation due to that. And then when we look at overvoltage, both at the inverter and the feeder level, we saw units trip off due to overvoltage, their high voltage ride-through mode. We lost that generation. We also did have some momentary cessation that we saw had tripped off or ceased generating megawatts for a few seconds and then came back about a minute later. And we also had some under frequency trips or reduction in megawatts, really faulty. Frequency didn't get that low, but their measurements caused them some issues. And you also see there's some unknown or not analyzed. And really, we'll talk a little bit more how important high resolution data is to be able to properly diagnose what the root cause for these failures were. And you'll see at the bottom, I also put a link to the NERC disturbance report where you can get all of this information and more relative to the event details. Obviously, it's difficult to cover all those details in this short time frame. When we look at the PLL loss of sync, these were two solar units primarily. And when we look at that in the terms of what inverter OEMs were involved, it was really one OEM in particular that had these issues. And what was interesting is that this inverter OEM has fixed this issue moving forward with new installations. But for the existing installations, while they have a fix, they're only implementing it upon request. So really, the awareness of this issue is important so that existing facilities can correct the issues, and new facilities are going to ensure that they have the proper settings come in from the beginning. But having this particular fault, this is something that was seen in California in previous disturbances back in 2017, and now we're seeing it in Texas as the solar integration continues to escalate within our interconnection. When we look at overvoltage, one thing that's really important to understand, we have rules, and those rules are that there's a no trip zone. So when voltage at the point of interconnection is within a particular range, your inverter-based resource should not trip off. What we were seeing is that the inverter, or at the terminal of the inverter, they were seeing voltages much higher than what was actually seen at the point of interconnection or on the system. So you have your inverter terminals, you have your feeder system, you step up past your transformer, and then obviously you have your point of interconnection there, or perhaps even a remote bus away. So they should at the terminal, they're seeing these higher voltages and they're tripping off at the inverter level while the system remains within the zone. This has been a persistent issue that's been, once again, seen in California, now in Texas. And one of the things is it's going to be very difficult to manage this because the inverter's responding to the voltage it's seeing. And in some instances, it's even driving voltage higher when the system has already recovered. So for example, the system sees the fault, recovers voltage, is back within normal ranges, but the inverter is seeing a voltage that's still low, or it's actually injecting megavar when you wouldn't expect it to, driving the voltage higher at the terminal or the feeder level and tripping itself off. And so when we looked at this in detail, there's a couple of things that we think we can try to do to help that by increasing some of the tolerances there. But some of the equipment has hard limits. And so the real takeaway here is that this solutions need to be driven by close coordination of the generating plant and include the vendor in those solutions, because ultimately the vendor has to start making tolerances within their equipment that allow for a wider range without tripping off these inverters due to high voltage ride through. This is also at the feeder level where we saw it. And one thing that was interesting here is a lot of times units were coming on, and while their equipment, for example, may be able to handle up to 1.5 per unit, because the ride through was at 1.2, they would set the relay settings right at 1.2 instead of utilizing their equipment capability. So it was a misunderstanding of the particular rules. It was a misunderstanding of that you really want to set it no lower than the requirements, but utilize your equipment capabilities so that you have more resilience in being able to ride through the disturbance. And so when we looked at this in particular, this is a education for some of these new developers. It's an education for the vendors. And we see these types of settings come from distribution type solar coming into the transmission system and bringing distribution type settings, IEEE 1547 type settings to the transmission system, where they really need to be more forgiving and utilize their equipment capabilities so they can be more resilient. We did have some legacy, older solar PV plants that experience momentary cessation. Our rules don't allow that anymore. And most of the solar OEM manufacturers understand that and design their equipment so that there's not momentary cessation. But we did have one facility in particular that went into momentary cessation. But you'll notice that the recovery time is still hindered. So if there is momentary cessation, we still would like those megawatts to return to the system as quickly as possibly, hopefully within 1 second. And for them to do that, there are other settings that have time delays. And sometimes those time delays or ramp rates back are just default settings that can be adjusted so that there's an improved performance after the momentary cessation occurs. So it goes into momentary cessation, the fault clears, and it's able to respond and recover back. That's what we want. And those are the changes that we have to work with the manufacturers and the plants to make. Now, when we look at some unknown causes, the real takeaway here is it is so important to have high resolution data. Simple SCADA data, 4 to 10 second type data, it's not sufficient. You need within cycles and potentially at multiple locations. At the point of interconnection, what was the system doing? Inverter oscillography, what was the inverter doing? Perhaps you have digital relays that can capture data, or fault recorders, perhaps on the low side in the feeder collection system. by being able to look at all these data sets, you're better able to understand the interactions between the inverter controls, the power plant controls, where was voltage on the high side versus the low side of the step-up transformer. Without that diagnosis, it gets rather difficult trying to understand what happened because it's all happening within cycles. To talk about the growth in ERCOT, why we're concerned. At the time of the event, we had about 7,200 megawatts of solar PV resources in ERCOT. This has grown quite dramatically within the last year. When we look at right now, we have over 10,000. So we've had almost 3,000 megawatts of solar interconnect within the last 6 months. When we're looking out to the end of 2023, potentially up to 25,000 megawatts of new solar PV resources may be connected. So obviously, if you have a risk, you lost about 1,000 out of 7,200, 15 to 20%. Obviously, as you expand your footprint of solar PV resources, if you don't do anything, you're going to have really large losses of megawatts, potentially leading to severe frequency disturbances. And when we look at the new standard IEEE P2800, it has a schedule coming into effect in the second quarter of 2022, and that may not be fast enough. So we're drafting rules as we speak within our region. We're creating an inverter-based resource working group or task force to look at this within our region to really try to adopt and implement as many of these guidelines and rules that NERC has given us to follow up on. So, and we are working with specific issues that we saw due to this event, as well as looking at the modeling. Both, we really, for these types of issues, positive sequence models do not seem to be effective. We're hoping that better models and the requirements around that for the EMT models may allow us to have a better screening process through the new interconnections that are coming on. And so we're trying to get that in line so that we can screen and catch these issues before the solar resources come and interconnect. Some additional observations, just to kind of highlight, we've talked through most of these things, but solar seems to be learning while wind has been already on the system for a few years, and we've kind of worked out some of those issues. But the solar resources are coming, and they're coming fast, and they're experiencing more issues right now like this. These are more major events. We're seeing regular disturbances, maybe 2 to 3 times a month, smaller losses of about 100 megawatts that are occurring on the system. So this is quite frequent that we're seeing unexpected reductions in megawatts due to faults on the system. It is also interesting to see potentially there's some issues between when an inverter goes into ride-through mode versus when the power plant controller is taking over. And so there's this handoff time period where the inverter is giving control back to the power plant controller, and the system is kind of sitting and doing nothing for a few cycles and then kicks into gear. And when it's kicking back into gear, sometimes it's lost its reference point, and it may actually be adjusting things contrary to what you would expect based on what you see on the point of interconnection system. So that's another thing that we're trying to better understand as we go along. Finally, just on the next steps that we have, we're working with the resources to try to implement corrective actions. And then we're looking at other solar resources that didn't experience issues but have the same equipment, same manufacturer, same vendor, and same model, and then working with them to make sure that they don't have settings incorrect. We're working, as I mentioned, quickly to try to implement new rules to tighten up our standards to make sure that we try to implement these corrective actions, not only for the existing resources, but for new resources to come. And once again, we're going to look at what our capabilities are for fault recorder and PMU data to make sure that we have high resolution data strategically positioned to be able to properly diagnose the root causes of these failures. So I'm going to pause there. I believe we have an opportunity for questions and answers later, but thank you for your attention, and I appreciate the opportunity to share this experience.
Thank you very much, Stephen. It's very interesting because, well, I have some direct questions for you now, because I can comment that in our system operator, we are facing for the next years a situation that can be close. We hope we do not face it in real time, because it's worrying, and we need to be prepared, because as in Texas, we are integrating a lot of solar PV. At the moment, we have around 6,000 and growing up every year, and with a high component of wind power. We have reached around 60% of hourly dispatch with solar PV and wind specifically. And our system, in a difference with yours, is very radial, very, very long. So for us, specifically in the north, where the most of the solar PV and wind is located, the strength of the system is very important. The short circuit rate is very important. We know that we have been very careful about this and how to anticipate certain elements to keep system strength. My first question is related precisely with the problem you experienced. In your case, according to the research you have explained very well, was it more related to frequency, under frequency, or under voltage in the regions where you experienced the disconnection of solar power plants?
Really, it was over voltage. The frequency failures that we saw were really poor measurements. They were not RMS values. And so the measurements, when we saw the high resolution data, saw frequencies much lower than what the system frequency was. And so when we looked into their measurement was poor going into the relay. And that's really what caused the under frequency failures we saw. Most of the issues that we're seeing were voltage related, and it's not the system. The system is responding just fine, but at the inverter controls, they are sensing voltages at the inverter much higher than what the system is. And whether that's related to the impedance difference between the inverter and the system, we're not sure. But they are, even in some instances, driving voltage higher on the low side than what it needs to. So voltage is already high, and they're injecting megavars, which is abnormal and what we wouldn't expect to see.
Yeah, some of the challenges you mentioned is related to the modeling and the system tools. Do you think that the use of EMT for modeling and to have the different inverter and plant models on a transient modeling analysis could facilitate the anticipation of this kind of phenomena compared to the traditional RMS modeling?
Yeah, I think positive sequence models have definitely played a significant role. I think when you look at inverter-based resources, the EMT models, the very detailed models, offer you both the ability to screen for things like this, because you actually get the control level type modeling. Obviously, you mentioned system strength issues. That's also going to be helpful when you're trying to really see how these systems are interacting and controlling with these inverter-based resources. That being said, it's really important that not only do you have EMT models provided, but that they're good models and that they match what's actually being implemented in the field. Oftentimes you may get modeling well beyond when they interconnect, and then you get equipment in the field, and if they don't set it to match the model, if you don't have validation, you may miss things where in the model it looks good, but because the field wasn't matching it, the field performance doesn't match what you studied. And so it's really important to both validate up front and then validate that they match the field for you to get a better reliability benefit.
Okay, thank you very much, Stephen. I'm going to continue with the other presentations, and after the complete presentations, we will have the opportunity to share with them some of their questions too. Thank you very much, Stephen.